fluid will flow. Okay. V is our shear force. And this is in Newton. Q is our first moment of area, which I'll teach you all how to find later on. Meter cube, sorry. And I is the second moment of area. So meter to the power 4. So if now we were to do a unit balance, okay? So you have V is in Newton, Q is in meter cube, I is in meter 4. The units is what? The units, as we just discovered, is in Newton per meter. Okay. So shear flow is in Newton per meter. Yeah. Then there's another term I want to introduce to you. It's known as the shear stress. Okay, shear stress. So the formula for shear stress, tau is our shear stress, is equal exactly the same as you see on top. So VQ and just divide by I and T. Okay, as I said, it's exactly the same. Okay. So it's the same thing. The V is the shear force, the Q is the first moment of area, the I is a second moment of area. So tau is our shear stress. And T is our thickness, or cross-section thickness of the beam, or thickness of the cross-section. Okay, so this is in meters. Okay, so if this would be in imperial, it would be in pound inch, it would be in pounds, inch cube, inch for pounds per square inch, and inch. Welcome to Canada. Okay. Okay. Now I've just written to you in words. Okay. The shearing stress is acting parallel to the surface, and the shearing stress is induced by the shear force. Okay. But how does the failure occur? What is the first letter of the shear stress? VQ over IT. Tau. Okay. So let's look at the failure by the shear force. Okay, failure by the shear force. I'll let you guys copy first. Anyone, any question so far? Okay.
So
yes.
What's that PSI?
Pounds per square inch.
Right, but like, what does that relate to? Is that shear stress?
Yeah, that's the units for shear stress.
Okay. Okay.
Sir, for the what do you call it now? The shear, the first diagram, what it was, shear flow.
Yes.
First diagram. Why is it that the P is applied from down under the graph? Why is the P applied from points? Basically, it's saying the load P is applied from length 0 right to length to final length.
Yes.
You're saying that load is applied across the entire.
No, it's at P.
P loads across entire part, right?
Yeah. So P is constant.
But on your diagram, on your diagram, it's only at one point. Is it just that you're taking that one point for example's sake, or That's what I'm kind of
what do you mean by 1 point?
on the diagram above, the example diagram you gave, where P is
Okay.
applied to the end of the cantilever.
Yep.
Is this
It's a point load.
that one?
Yep, it's a point load.
But on your diagram, is that showing a point load or is it showing
the
a
shear force
constant load
diagram
over the
is
entire?
constant throughout the whole surface.
Oh, it's okay.
Okay.
Sir, I have one question.
Yes.
So in a diagram, the load is applied on point B, right?
Yes.
But bending moment diagram, the maximum bending moment is on point A. It shouldn't be. It should be point on it should be on point B because our load is applying on point B and the moment.
Okay, Gurpreet, let me ask you a question.
Yeah.
And okay, I like Gurpreet's question. Okay. If P is applied at point B, why is the bending moment the highest at point A? Okay. Then I'll ask everyone, where will the structure fail? At point A or at point B?
Point A.
There you go. You answered that question already.
Okay. Now it makes sense. Yes.
You answered that question already.
Okay. So the bending moment is maximum where the
because bending moment, I'll tell you what, bending moment is equal to force times perpendicular distance, and this is the perpendicular distance. Yes.
Yes.
The greater the perpendicular distance, the higher the bending moment.
Oh yes.
Yeah. So that's why the failure happened at point A.
True. I was thinking the opposite way. Like
it's okay. It's okay because I don't think
deflection would be the opposite way. That's how the deflection would show the opposite way.
Yeah, deflection will show the opposite. I think when you all do static and dynamics, you all never look at shear force diagram, bending moment diagram. The last time probably you did this was in your college. Okay, so it's okay. You need to clarify all this before we go. Okay. Right. Now, more confusing. Okay. Why I say more confusing? Because I was also confused. Okay, when as I said, this is the 7th time I taught this topic. Okay, I've taught strength of material since 2008. Okay, but this is the not the 7th time, the 21 time. Okay, because every year then I can really capture what is going on. Okay, after I taught it for so many times, okay, for the past 7 years, then I really grasped the concept what's going on. Because how I could grasp the concept, because I did a lot of problems at doing consulting and also doing design work. Okay, then I really understand the concept. Okay, so let's look at this. Okay, let's look at failure by shear force. Okay, failure by shear force. Okay, and let's look at the deformation pattern. Okay, let's look at the deformation pattern. Now I'll go back up, okay, to the first diagram I've drawn. Remember, I told you guys what? We are calculating the failure or the area of concern is the yellow part, right? The part that's highlighted in yellow. But this surface, the one I color in blue, is very important. Okay, the one that I color in blue, okay, this surface is where failure surface. And you guys will tell me, Eugene, go to hell, man. You just told us that we are calculating the yellow surface, but the failure is on the horizontal surface. How is this what? Shear, okay? Let me explain to you once I go further and you will understand the concept, okay? But the first thing I want to highlight is what? The yellow surface is what we calculate. or analyze. The failure surface is not that surface. It's the horizontal layer. Okay, it's the horizontal layer. Okay, now let me elaborate. That's why this topic a lot of universities just okay. Let's forget it. No, it's not that difficult. Okay, so let's now construct the deformation pattern. Okay, we will construct the deformation. So this is still our cantilever. Okay, and this is our deformation pattern. Okay, so I'll try to draw layer 1, 2, 3, 4, 5. Okay. Okay. Right. So at the end, they look like this. This is amplified. Okay. Okay. This is amplified. Right. It's like if you have a deck of cards. Okay. You hold a deck of cards at one end and you bend. You see this. It's exactly the same like a deck of cards. Okay. Right. So first of all, let's look at what I described regarding the bending moment. Okay. So what I've done is a deformation pattern. If you look at the bending moment diagram, right, I concentrate more on the negative bending because the bending moment is set face, right? So if I cut this into half as in a cantilever beam, the bending moment looks like a set face down here. Okay, so look at our deformation pattern. That is how it looks. That's why we focus on the bending moment in the negative. Okay, so that one we put to bed. Now the next thing I want to take note is if we were to look onto this surface, okay, if we were to look on where the slip occur, okay, so I will amplify that view down here. Okay, so you have horizontal, right? This is what you see. And you realize that we have a certain, we see a slip. Okay? So this is our delta. Right? Delta is the distant move or deflection induced by the shear force. Okay, right? So if we were to look at this distance over here, I'll use a different color. We call this A, right? That distance A before deformation and after deformation did not change a lot. Okay, that distance A, okay, A magnitude did not change before and after deformation. Okay. Where else the delta over here, delta was not there before deformation. So delta, okay, delta was 0 before the load was applied. Okay, so delta will have a magnitude with higher loads. So the higher the load, the bigger the what? The delta. Right? So now, coming back to the first diagram. Where's delta? The yellow surface